Hello everyone. Today I want to go over the Kinetics and Equilibrium review pack. So here are the answers to the first 24 questions. I told you to skip questions 1 and 2, so don't worry about those right now. And here are the answers to the PE diagrams worksheet on the back page of this pack. Let's take a look at these and we'll go through everything. All right, so questions 1 and 2, as I said before, we skipped. So now let's take a look at the next couple of questions, which deal with our entropy, which remember is our measure of disorder or our sloppiness. So if we look at number 3, as a lump of sugar is dissolved in a beak of water, the entropy of the sugar and water system, the answer is A, increases. And remember why, because we're going from sugar and water separate, so the sugar is a solid, the water is a liquid, and now we're combining them and we're forming a solution. So remember our order of increasing disorder as we go from solid to liquid to solution to gas. As we go across, our level of disorder, or our entropy, increases. So solid is the most organized, all the way up to a gas, which is the most unorganized. So remember, think about entropy as your sloppiness or your measure of disorder. Okay? Number 4, chemical reaction must be spontaneous if it results in an energy. So remember what spontaneous is. Spontaneous means it happens all by itself without any outside intervention. So what we want to remember here is nature likes stable and sloppy. Nature likes stable and sloppy. So what is going to be stable? You want a low PE, low stored energy. So when do you get a low stored energy? When there's a loss of energy, which is losing energy, exothermic, right? Which is exothermic. Energy is exiting the system. So nature likes exothermic systems and nature likes sloppiness, disorder. So you're always going to be spontaneous when you're resulting in a loss of energy and an increase in entropy. So the answer to that is C. All right, and then number 5, ammonium chloride dissolved. The reaction occurs in the beaker is, so 2 things here we're looking for. So the temperature decreases. So remember what that means. If it gets cold, that's going to be endothermic. So endothermic processes get cold because remember, you're absorbing energy, you're gaining energy, but you're gaining it from the surrounding matter. So the surrounding matter loses energy and the temperature decreases. And then it's going to be spontaneous. How do we know it's spontaneous? Because we didn't have to do anything to get the reaction to occur. Once we combine those substances, they reacted. All right? So that's how we know it's spontaneous. You don't have to do anything to get the substances to react with each other. Once they're in contact with each other, they react. So let's move ahead to number 10. I'm not going to go through all of these. I'm just going to go through the ones that I think need a little bit of discussion. Number 10, all we want to really know here is vocabulary. Equilibrium. Remember what equilibrium means? At equilibrium, remember what's equal at equilibrium. The rates are equal and the concentrations are simply constant. Right? They don't have to be equal. They can. It doesn't matter. So at equilibrium, remember what's equal. The rates are equal and the concentrations are constant. The word dynamic here just means that it's always happening, right? It never stops. So remember, these equilibrium reactions, they never stop. These reversible reactions, all we do is we get to a new equilibrium, but they're always going. They're always going, they never stop. All that happens is you get to the point where the rate of the forward reaction equals the rate of the reversible reaction. Therefore, there's no observable change, right? That was our analogy of students in the classroom versus students in the hall, right? If every minute one student leaves the class, but every minute one student comes in, you're not going to notice any changes in the amounts of students in the classroom versus in the hall. So that's where our concentrations are staying constant. They're not changing. Next up is number 13. So sometimes it's a little tricky to see what the stress is. So this one's a little bit tricky here. So in the equilibrium, H plus and CrO4 minus 2 makes Cr2O7 and water. Adding NaOH. So it results in an increase in the concentration of what? So it's saying, okay, this is our stress. How has the system responded? So remember the 3 steps in Le Chatelier's. Stress is applied, the system responds by shifting, and then how have your concentrations changed? So what we want to think about here, though, is what is the stress? So NaOH is not in this reaction, but NaOH is a base, and it tells us here that it breaks up into Na and OH. So we don't care about the Na. That's not in this reaction. But OH isn't here either, but think back to acids and bases. OH joins up with H to form water. So by adding a base, remember our seesaw with H and OH, right? Let's think back to our seesaw with our H plus and our OH minus. If we add OH, what does that do to our amount of H? It goes down. So our stress is really a decrease in H plus. So now it's pretty simple. Once we know what the stress is, you want to remember, you want to shift away from what's added and towards what's taking away. So what are we doing? We're taking away H. So we want to shift towards what's taken away, which means we shift left. So what does that mean? Whatever you go towards gets bigger, and whatever you go away from gets smaller. That's it. So what's the answer to number 13? The answer is B. We're going to result in an increase of our reactants. So in this case, CrO4. And also notice, right, what's happening to our H? It's going up. So the stress was we removed H, and look what ended up happening. We're putting H back. So remember, the goal of Le Chatelier's is always to reduce the change. Reduce the change. So whatever that stress was, remember, we don't like stress. Stress is bad. We want to get rid of the stress. So if we took H away, you want to respond in a way that's going to put H back. So what do? We shifted left, which means we're speeding up the reverse reaction and making more of this stuff. So this goes up, and then these go down. Why? Because we're consuming these guys to make these guys. Right? Remember our analogy of sandwiches. I got to use up bread and bologna to make more sandwiches, or vice versa, right? So next up, number 14. Increasing the temperature usually increases the rate of a chemical reaction. This is best explained by C. So this is simply collision theory, right? Why does increasing the temperature increase the rate of reaction? Because it's all about frequency of effective collisions. More collisions, faster rate. Less collisions, slower rate, right? What is an effective collision? That's when old bonds break, new bonds form, when the particles collide with the right energy and in the right orientation or position. Next up, number 15. If a catalyst is introduced into a system, the heat of the reaction is going to do what? The answer is C, remains the same, but think about why. All right, here's a PE diagram. So remember what a catalyst does. It lowers the hill, right? But by lowering the hill, remember what we're affecting. All that we're affecting is the amount of energy needed to get up the hill, our activation energy, right? So in both directions, we're affecting that. So we're affecting how much energy is needed to get up the hill, and we're also affecting the amount of total stored energy in that activated complex, right? That intermediate structure that forms when the particles collide. But notice what's not changing, right? Our delta H, our difference between the reactants and the products, is not changing, right? It's staying exactly the same. So the hill getting higher or lower has no effect on the difference between the reactants and the products, right? It's not changing. Look at the visual. No matter how high or how low this hill is, it's going to have no impact on the difference between the reactants and the products, which is our delta H, right? Notice what doesn't change also. Your PE of your reactants and your PE of your products. Number 16 is again dealing with our catalyst. So a catalyst increases the rate of a chemical reaction by, what does it do? It decreases the required activation energy. So remember though, that decreases that activation energy in both directions. See, it's lowering the activation energy by the same amount. So it's speeding up the forward reaction and it's speeding up the reverse reaction in the same amount, by the same amount. So it doesn't affect your equilibrium at all. So it's like saying, okay, instead of every minute one student leaves the classroom but one student comes in, now every minute two students leave and two students come in, right? It doesn't affect our equilibrium. There's no shift. There's no change in concentrations. But now if the stress is applied, the system is going to respond more quickly because the catalyst has made it easier to go in either direction. Number 18 next. For the equilibrium system, as the temperature increases, what happens to the amount of oxygen? So again, temperature increases. So that's our stress. So we're adding heat. So remember what that means. You want to shift away from what's added. All right, so if we're adding energy, here's our energy. We want to shift away from the energy. So we want to shift left. Remember what that means. Whatever you're going towards gets bigger, and whatever you're going away from gets smaller. All right, think about apparent size. If you're moving towards something, it appears to be getting larger, and if you're moving away from something, it appears to be getting smaller. So once you figure all this stuff out, then you could answer any question that's being asked in the problem. So figure out your shift, and then you always know whatever you're going towards gets bigger, and whatever you're going away from gets smaller. So what's happening to oxygen? Oxygen is increasing. Not so bad. Next up, number 20. A rise in temperature is going to do what? So remember, the goal. Reduce the change. Right? So if I increase the temperature, that's my stress, I want to respond in a way that's going to bring the temperature back down. So I'm going to favor the endothermic reaction because remember, endothermic gets cold. So that's going to bring the temperature back down and reduce the change. Okay? Next up, 21. Which change would result in? So these are the trickier ones where they're giving you the outcome and asking you for the stress that caused it. So we want to result in an increase in SO3. So how do I make more SO3? I want to shift right. Okay, so now it's asking me which of the following stresses is going to give me the desired shift. So now we got to go through each stress and see which one gives us a right shift. So let's go through each one individually. Increasing the pressure. So remember how pressure works. Pressure, you want to always go in the direction that's going to reduce the change. So if I increase the pressure, I want to go to the side with less gas particles because I'm going to get less collisions, and that's going to bring the pressure back down, reduce the change. So you got to count your gas particles. So anything with G's is what we're looking at. We don't care about anything that doesn't have a G there. So 2 SO2s plus 1 oxygen means I have 3 gases on the left and only 2 gases on the right. So you got to count your gas particles on each side. Okay? So 3 gases on the left, 2 gases on the right. So if I increase the pressure, I'm going to want to shift right to the side with less gas particles because that's going to bring the pressure back down. So that's a right shift, right? But what is increasing the temperature going to do? Increasing the temperature, we want to shift away from what's added. So that's going to result in a shift to the side, a shift left, right? Away from what's added. So the temperature is going to give us a left shift. So that's no good. All right, another way you could think about it, increased temperature, is always go to the side with more gas particles. When you talk about you're away from what's added and towards what's taken away, this is the side that's going to be most affected, right? So go to the side with the most gas particles and do your away from what's added and towards what's taken away in relation to that, right? So if I'm increasing the pressure, I want to shift away from what's added. So if I'm adding pressure, I'm going to shift away from the side with more gas particles, right? So you can, that's kind of another way to think of it if that helps you out. And then it's kind of a little bit more uniform in terms of your away from what's added and towards what's taken away. So with gases, always think about the side with more gas particles. So that's the side that's most affected, so you can do your towards and away in relation to that. So B, increasing the pressure, we did that already. But now decreasing the temperature, then we're going to shift towards what's taken away. So both of these stresses are going to give us a right shift. So that is most likely our answer. So let's look at the other ones. Decreasing the pressure, well, we know. Decreasing the pressure means then we're going to shift towards what's taken away. So that's going to result in a left shift. So our answer is definitely B. All right, these are the trickier ones where they give you the outcome and ask you for the stress that caused that outcome. So you got to kind of think of these backwards. So take a second and make sure you're answering these correctly. Next up, 22. The answer is C. And remember why. A pressure increase, as pressure is increased, why do the number of moles of HI remain the same? Because we have 2 moles of gas on the left and 2 moles of gas on the right. So neither side has more or less gas molecules. So a change in pressure, neither side is more favorable. So the system's not going to respond to any change in pressure because shifting left or right isn't going to reduce the change. So when you have equal amounts of gas particles on each side, the system is not going to respond to any changes in pressure. 23, in which reaction would an increase in pressure produce an increase in the amount of product? So now you got to kind of, again, look at these and say, all right, which one is going to increase the product? So how do I increase the product? I want to shift right. So which of these is going to result in a shift right when we increase the pressure? So we got to count our gas particles. So A has 0 moles of gas on the left, that's a solid, and only 1 mole of gas on the right. So So if we increase the pressure, this is going to result in a left shift, right, away from what's added. So we're going to shift left and go to the side with less gas molecules. So let's go to B, solid. So that's 0 moles of gas on the left, 1 mole of gas on the right. So same as A, we're going to shift left when the pressure's increased. C, 1 plus 3, so that's 4 moles of gas on the left and only 2 on the right. So now this side has more. So we want to shift away from what's added. So if we're adding pressure, you want to go away from the side with more gas molecules. So this is the one that's going to shift right. So that's our answer, right? You want to go to the side with less gas particles because that's going to reduce the change, less collisions, bring the pressure back down. All right, let's take a look at D just to see and make sure that we're correct. So 1 and 1, 2 gases on the left, 2 gases on the right. So this is one where we have equal amounts of gases on both sides. So the system is not going to respond to any change in pressure. Pressure is the trickiest. So if you can understand that, then you're doing pretty well. Last question. This was really a review from back in solutions, so you're not going to see this on the test, but it does help to go over this stuff because chemistry is cumulative. So as the pressure of a gas increases, the temperature remains constant. What happens to the solubility? So remember, gases are most soluble at low temperature and high pressure. Think about soda, right? How do you like your soda? You like your soda cold, and it's stored under pressure to keep that gas dissolved. So as the pressure of a gas increases and the temperature remains constant, solubility increases. So just remember about your gases. We like our soda cold. So gases are most soluble at low temperature, high pressure. So last thing we're going to do is go through the PE diagrams on the back page of this review pack. So let's go through these. I posted the answers before, but let's just talk about it. So number 1, is the reaction exothermic or endothermic? So remember, is energy exiting or entering? So it's the visual. You say, all right, we're starting up here, we're ending down here. So we're ending up lower than we started, so energy is lost. Energy is exiting the system, so that's how we know it's exo. Right? What is the delta H? So when they give you values over here on your y-axis, you can actually calculate these numbers. So remember, your delta H is heat of the products minus heat of the reactants. So it's always products minus reactants. So 10 minus 40 is going to give us negative 30. Right, negative 30 kilojoules. Number 3, what is the value of the activation energy? So remember what our activation energy is, how much energy it takes to get up the hill. So you're starting at 40 and you got to get to 60. So you only need 20 more kilojoules. Number 4, what's the PE of the products? So your products are over here. PE is always connecting your x-axis up to the line. So there's 10 kilojoules of stored energy in our products. And then what's the PE of the activated complex? Remember where the activated complex is? It's top of the hill. So how much total energy is there at the top of the hill? So 0 up to 60. So that's 60 kilojoules. It's not too bad. All right, next one. This one's got a little bit more information on it. We've got a catalyst now lowering the hill. So just pay attention to what's being asked about and make sure you're answering the question appropriately. So again, exo or endo, easy. Look at the big picture. Are you ending up higher or lower than you started? So in this case, we're ending up lower, which means energy entered the system. So that makes it endothermic. What's the value of activation energy of the uncatalyzed reaction? So that's this. If it doesn't say a direction, you assume we're talking about the forward reaction, right? If it's talking about the reverse reaction, it'll say the reverse reaction. So the activation energy of the uncatalyzed reaction, so we're going from 10 up to 35, so that's 25 kilojoules. So it takes 25 more kilojoules to get up the hill. We're at 10, we got to get to 35. 8, what's the value of the activation energy of the catalyzed reaction? So now we only got to get up to here. Right? So 10 to 30, that's only going to be 20 kilojoules. So it's not too bad, but just make sure you're reading the question and answering what's being asked. 9, what's the PE of the activated complex of the catalyzed reaction? So here's the catalyzed. So how much stored energy is there? So we got to go from 0 up to 30. So that's a total of 30 kilojoules of total stored energy. And then last one here, number 10, how does the delta H compare to the delta H of the uncatalyzed reaction? So it is the same, right? The delta H is not affected by the hill. Remember that. All right, there's my delta H. The product and the reactant's PE never changes. Those are the same. So the size of the hill has no impact on our delta H. Right? What is our delta H? If we had to calculate it, 25 minus 10 gives us 15. Right? But not just 15, positive. Don't forget the sign. So if we had to calculate the delta H here, it's positive 15 because it's endo. Gaining is good. Gaining is positive. Last one here. So there's a lot of information here. So don't worry about how they identify each part. You just want to look for what's connecting the right parts. And now they kind of move things around here to make it a little bit confusing for you. So if you can get through this and focus in on the appropriate parts, you're doing great. So 11, the PE of the activated complex for the uncatalyzed reaction. So top of the hill. So we want to go from here to here. So which arrow is doing that? That would be arrow H. Number 12, activation energy of the forward catalyzed reaction. So forward. So we want to go from here up to here. So which arrow is connecting those 2 points? That would be E. Right? So look for which one is connecting the appropriate points. Filter out all of the other unimportant information and focus in on what the question is asking about. 13, PE of the products of the forward reaction. So these are my reactants. So here's my products. So that would be letter B. Number 14, activation energy of the uncatalyzed reverse reaction. So that's G. 15, PE of the activated complex for the catalyzed reaction, PE of the activated complex for the catalyzed reaction. So now how high is the lowered hill? So PE, x-axis up to the line. So that's I. Number 16, activation energy of the uncatalyzed forward reaction. So now I want to get from here to the top of the hill. That's letter F. 17, the delta H, right? Heat of the reaction is the delta H, change in heat, change in energy. So that's the difference between the products and the reactants. That's letter A. 18, activation energy of the catalyzed reverse reaction. So we're going backwards, catalyzed. So the lowered hill, how much energy does it take to get up the lowered hill going backwards? That's letter C. And then the last one, the PE of the reactants for the forward reaction. That's pretty simple. That would be letter D. All right, so if you're able to get through all of those and get them correct, then you're doing pretty well with the PE diagrams. So that's it for this lesson and going over this worksheet. Hopefully that was helpful, and I'll see you all next time.